I'm Gary Bradski. I'm interviewing Pietro Perona. He's a longtime professor at Caltech. He started a PhD at UC Berkeley and followed with a postdoc at Berkeley and MIT, and became pretty young and early professor at Caltech. Among the brag sheet, he's a foundational person in computer vision, but his NSF Young Investigator Award, Longue-Higgins Prize in 2013, Konderik Prize for Fundamental Contributions in Computer Vision. I first met Pietro when I was getting interested in dynamic processes, and he had anisotropic diffusion that became a well-known program. Has done work in categorization. Some of the things he started as Visipedia and the Caltech 101 and then 256, which became kind of foundational in image databases. So welcome, Pietro. Yes. I guess we can start. I'm going to kind of start a little bit of career. I'll let you save that for a lot of it for your biography, but I'll just go through some of that, and then we'll get on to some of your work, and then I'd like to get into current work and speculations about the vision system and how the brain works, whatever. We can go into philosophy and whatever. So. You started, your PhD was in Berkeley. Was that in vision, or how did you become attracted to the field?
Yeah, it was serendipitous. So I I came to Berkeley and I thought I would work in controls. I had liked controls. I liked math. So as an undergrad, I had been attracted to controls for the where you can see the power of mathematics to describe things that happen in the world. And during my first year, my advisor then, Shankar Shastri, gave me a paper to read where people were using tools that were, belonged mostly to control theory, Markov random fields, to analyze images. And it struck me that you could take something as messy as an image and think that you could build a software program that could analyze the image and understand what is in the image. And that was, by the way, the thesis of José Luis Marroquín, who was co-advised by Sanjoy Mitter and Tommy Poggio at MIT. And for me, it was a revelation to see how fairly simple formalisms could make sense of fuzzy, complicated informations that are there in images. And so I got hooked on the computer vision question. And so soon I left behind the method, which, by the way, was very nice. The Markov random fields have had a lot of good uses in vision, but I got hooked on the question of how can we build a system that can analyze images and extract meaning from images. And I must say I was always very attracted by images. My mother was very fond of art, and she took me through all possible museums in Europe. I enjoyed, first of all, I suffered through what felt like endless marathons through the Louvre, Uffizi, and so on. But I became very interested in art, and so the possibility of working on images was very appealing to me. I'm just attracted by images, and I thought that putting mathematics and images together was an amazing, terrific idea. And so since then, I've been very fond of this field.
And then you went on to postdocs at Berkeley and then MIT. What were you working on then?
Well, at Berkeley, so first of all, in my PhD, so I worked on image segmentation using diffusion equations. So that was another another little discovery. How using simple PDEs you can do so much to understand an image. And so again, it was one of those moments of joy in which you see something simple doing something that appears to be complex. Then, so towards the end of my PhD, I started becoming interested in using mechanisms that you see in the visual system, namely Gabor functions, to analyze the content of images. And the hope then was to come up with a revisitation of Mars idea that the way to do vision is to first extract simple descriptors and then aggregate those descriptors into more complex descriptors and finally arrive at the meaning that is hidden in images, which at the time it felt like is visual categorization, visual recognition. And so I started studying the properties of early visual filters and got interested in how physiologists could measure those properties in biological systems, typically in the cortex of cat and monkey. And so when I was at MIT, I was studying how to steer these filters, and that's something that I got interested in from Bill Freeman, and Eero Simoncelli was there working also on the same topic at MIT. How do you steer these filters in a space of sort of scales, orientations, parities, even, odd filters, frequency, tuning, and so on. And so that was useful for example, finding boundaries in images. And then when I came to Caltech, I decided that I should not continue on what I had done before because I risked putting all of my students into the local minimum of whatever I had done for my PhD. And so I decided to branch out. I realized that vision was far from being solved, and so it was better to lunge out in a million different directions and put each student on a different problem and see what stuck and what came out of it. And so my first few years at Caltech were a period of exploration. I don't know that I did anything particularly useful, but at least I trained myself into many different areas of vision, and I got unstuck from my initial condition. And towards the end of my first decade at Caltech, I realized that visual categorization was really interesting, and nobody was interested in it, but I was, and so I decided to study it. And that's why we collected the data sets of Caltech 101 and Caltech 256. It was a time when...
Yeah, that started with Fei and Fergus, right? Yeah. I forgot to mention that one of your big contributions is so many fantastic students who have gone everywhere. Fei, Jean-Yves Bouguet is like director at Oculus now, and many students, Silvio Sarvanis, and I don't know, I'm missing a lot now.
There are Stefano Soatto at UCLA, for example.
Oh, yes.
Yeah, Fei and Silvio at Stanford, Lee Zelnick, who was a postdoc, Max Welling, who is now at Amsterdam, and so on.
Yeah.
And so, that's not my contribution, it's their contribution. And it's just lucky that if you're in a good right amazing people come along and you get to work with them and you benefit from their ideas. Right. And in some ways, as everyone who is a professor knows, the key benefit of being in a good university is young people who are smarter than you, and they challenge you all the time, and they ask you to justify why you believe this, and explain it to me.
Yes.
And then, if you're believing something that is not true, you discover it pretty quickly. And so they help you debug ideas and challenge you to get unstuck from silly things you're believing and looking at the real questions and so on. So, but so at that time, I think maybe the big realization at the end of the first decade, at the end of the 1990s, was that people working in visual recognition were working on mostly individual objects. And so, can you recognize the logo of Coca-Cola or the box of your Rice Krispies or the some type of aircraft and so on?
Right.
But truly, the interesting question was visual categorization. How can you tell frogs and cell phones and people and dogs? And at the time, we were very engineering oriented and analysis oriented but it was clear that for visual categorization, one would have to move on to learning. There was no other way to go about it. And saying it now feels like, okay, yeah, of course. But at the time, if you look at the proceedings of conferences at the time, 90% was geometry. And then the 10% that was recognition of individual objects. And so
very handcrafted.
Yeah, and so
well, also the features were
and
handcrafted.
there were people working on faces, and so they were handcrafting detectors for eyes and mouth and ears and so on. And so people were handcrafting components and hoping to put them together to analyze images. But then it was clear that that wouldn't scale. So there was an estimate at the time by Irv Biederman that people recognize about 3,000 categories really well, the entry-level categories, and about 30,000 categories in general. And you can see how that would be the case, because if you think of all the Chinese characters that people can recognize, it's about 10,000, 20,000. And then all the faces of people it's a few thousand and so on. So it's in the thousands, and if you sum up all of these thousands, you get the tens of thousands. So it would simply not scale to handcraft detectors. And it makes a lot of sense for faces and maybe automobiles because they're so special and so valuable. But if you have to move on to birds and dogs and cats and mushrooms and so on, how do you do it? And so what they thought was, well, let's start collecting, the internet was available and you could search for images. So let's start downloading images and build image data sets. And so I thought if somebody wants to claim that they're working on visual categorization, they should be able to, with the same piece of software, without changing a stitch in their software, they should be able to recognize mushrooms and dogs and trees and so on. And again, this sounds obvious today, but it was not at the time. And so that's why we collected first Caltech 4, then Caltech 7. And then I remember one day telling Fei, okay, that doesn't cut it. 7, we're still overfitting probably. Who knows? We're doing automobiles, spotted cats, airplanes, faces. Maybe we are overfitting. Well, let's have more. And she said, okay, how about 15? And at the time it was a big piece of work to download and sort out the images. And I said, no, more than 15. And she came to me and said, how about 20? And so that somehow ticked me off, or I thought, oh, she's being lazy. And so I said, no, let's do 100. And so she went off, and 2 months later she came back with 101. And it's supposed to show me that that she wasn't...
She exceeded expectations.
So what we did, we took a visual dictionary to select... image categories that have a visual correlate. So you couldn't select a category like the economy that, you cannot depict it, but, mushrooms. And so we went through it, and then we saw which images we could download that had enough representation on the web, and then we hired Caltech students to sort them, and so that's how we collected Caltech 101. So that was quite good. So from Caltech, so when we put it out again, most papers in conferences were about geometry, and within 2 or 3 years, you could see the whole sea change of people starting to work on visual categorization, and I think, I tell my students now, so something we did was our initial approach to Caltech 101 was so bad, it was only 18% correct, which is still better than 1% correct, which is if you do random choice, but it's not great. And so simultaneously we put out a data set that people could use for training and testing, and a paper that people felt they could do much better than us. And so somehow that probably got people more interested. They thought, okay, can do better.
Yes, it's always good to do a paper that can be exceeded because you generate 1 million citations. It's a very good trick to become a professor. I really think it was foundational in spurring a learning-based approach, because at 101, it simply overwhelmed any handcrafting. So that was an important event. I think, you went on and did Visipedia. I wanted to, well, we can start talking about current work or things you're interested in.
Yeah, I'm happy to talk about Visipedia if you want a little bit. I can
Sure.
tell you how it was born. So, yeah, so Visipedia is a project that Serge Belongie and I started, and it's something funny happened. Serge came on sabbatical to Caltech, and that was the end of 2008. And simultaneously, or almost simultaneously, I went on sabbatical in Italy. But then in the brief interlude in which we were both at Caltech, we started talking about the next step in visual categorization. And something that was clear to us was that just downloading pictures from the internet, just because you wake up one morning and you say, I want aardvark and I want abacus and so on, it doesn't cut it. It's not reality. It's just computer vision people playing. And so if we wanted to know what the real questions were, we should go and talk to people who need to do visual categorization on a large scale and see what kind of images they have to deal with and what are the challenges that they face. And so we thought, okay, we have to find a community of people who is going to engage with us and who has interesting images to classify. And so we went through 10 or 20 different hypotheses. And underlying all of this was the idea that so the computer vision people are not the experts in almost anything. And so there is this question of the flow of information between experts and machines. And we wanted to understand not only how machines can do visual categorization, but how can machines learn from people. And so that's why we wanted to find a community that would engage with us. And so in the end, we chose birds and bird watching. And the reason was we thought, first of all, the pictures are pretty. Second, there are tons. Third, bird watchers go out and they buy expensive cameras to take these pictures, and they are now uploading these pictures on servers in order to exchange pictures. And so they must be technically sophisticated and they're ready to interact with any web page we may put up on the web to talk to us. And so we came in touch with the Laboratory of Ornithology at Cornell, the Lab of O, and there are a bunch of really good people there. And so we started working with them, and it was great because at the time they just were about to deploy a service through which they would allow birders to upload their pictures to the Cornell site in order to obtain help in classifying the birds. And they were getting maybe 30,000 pictures a week, and soon it became 50,000, 60,000. And at the time, Grant Van Horn was starting his PhD, and Grant had been an undergraduate with Serge and then came to Caltech for his PhD. And Grant was very hands-on, and so Grant helped us build an iPad tool and then a website that would allow people to recognize these birds automatically. And so we could work with Cornell on this. And there are 10,000 categories of birds. And so that was fantastic. And so we had access to experts who were willing to label the images, so we could measure how many mistakes do experts make, and we could measure on Amazon Mechanical Turk how many mistakes do people that are not experts make. And we could wonder about how does a machine know who is an expert and who is not, and how does a machine measure how much to trust a given person or a given label. And so, so there were maybe 2 or 3 main realizations that came out of this project. So one was that really the paradigm in which machine learning people and computer vision people work is not correct. So we think of the machine as a tool like a plow or a tractor, and there is an oracle that is labeling the images, and we have to feed these precisely labeled images into the machine, and the trick is figuring out what's the right learning algorithm to use, right? And in fact, the real situation is the opposite. The machine is the agent, and the machine has to, nobody is an oracle because the knowledge is not owned by any single person. Knowledge is owned typically by communities. There is no single birder who knows all the birds, no single pathologist who knows all the types of cancer and so on. So the knowledge is in a community, and the machine has to talk and has to socialize with a community of experts, and it has to use images as a means, as a vehicle to obtain that knowledge from the experts. And so it has to figure out who knows what, and it has to develop trust in the people. And so there is no oracle anywhere, and there are going to be a lot of mistakes, and yet the machine has to be able to socially interacting with people, build up its own knowledge, and know how much to trust it. That's the question. So
and many categories are actually a joint community decision, because when you begin to analyze a category, it's really there's not a God-given fact, right?
That's right. That's right. And so for birds or animals, we know from genetics that there is a scientific basis for categories, and that's a species. But then in many other domains, it's just a folksonomy. So maybe fashion, types of clothing you may wear, what look do you have today, and so on. The names for those things come from people. And so you have to be able to work also with folksonomies and, get information from the crowd that is completely arbitrary. And yet to have to reconcile different ideas. So that was one teaching. Second one is the world is not a uniform distribution like in Caltech 101 or ImageNet, where you have 1,000 pictures for each one of 1,000 categories. The world is a long tail distribution. And so for some categories, and so I'm going back to birds, say the bald eagle, you have hundreds of thousands of pictures in the Labovo archive. And so that you can learn really well. But then you have some birds, like the pileated woodpecker, for which there is no real photograph of the animal in the wild. And so you have this long-tail distribution, and the machine has to learn some common principles from the categories where you have a lot of information. And then it has to make do and become good at recognizing categories for which you have very few training examples. And so people are really good at that. And a birder, you can show them 3 or 4 pictures of a new species they've never seen before, and they can get going pretty well from that. And as you know, for machines, we need thousands of training examples to get expert level performance.
Right.
And so that's another learning. And so
this goes into this kind of zero shot learning or one shot. I remember reading about a mountain biker who was attacked by a mountain lion, and I go, how does the lion even know where the head is? Like, what is this thing? So there's something very universal about learning, that it can deduce something that's never existed in the natural world, right?
That's right. And so, I mean, by now, everybody has realized that that's one of the main problems in visual categorization and machine learning, which is how do you learn from few examples in the limit n equals n, limit of n going to 0. And we are still struggling with that, but it's definitely something that people are making progress right now with self-supervision, some unsupervised techniques that have come up recently, and so on. So that was another learning we got out of that collaboration. And the third one maybe is how to interact with large communities of annotators or experts, and again, how to infer their abilities and how to make use of those to get a level of confidence on some deductions that a machine may make, namely how, what kind of label to give to a machine. And so here I should mention a collaboration with the California Academy of Science. They have an app out called iNaturalist, which anybody can download to their cell phone. I don't know if you use it. And so that's another piece of work that Grant Van Horn did. And so he embedded himself with them. And so he both built the computer vision system that is behind their recognition. And it handles, at the moment, it's about 50 or 60,000 species of plants and animals. And also he built the statistical backend that estimates for each person who interacts with the system, what are they good at? Are they good at butterflies? Are they good at lizards or at nothing? And so how to combine different people's opinions into a final verdict. And is the verdict safe enough that you can make the image become part of the collection from which the machine learns? And so somehow it led us to what you might think of it as the first online system that people use that is for real, namely the machine there is just interacting with the crowd keeps labeling images, the machine, once it reaches sufficient confidence that the labels are correct, it incorporates those training images and labels into its training set, and it retrains itself. And so you have here maybe the first example of a big scale system that interacts with the crowd and it trains itself, it learns by itself. And so that's something.
Earlier work in crowdsourcing.
That was kind of the inception of crowdsourcing. I think, looking a little bit back, like today's people don't really know, how hard and limited it was. When I did my PhD, I had to beg to timeshare a professor's camera. There weren't digital cameras at the time. It was hard to record. And then up and up these image databases. This Caltech was really the first one. It was unusual to have more than a dozen images or so to work with. It's hard to realize from today that, with Google and a billion images available everywhere, it's a very different world. I think the cell phone revolutionized a lot in computer vision also.
I think my PhD thesis was all the experiments were done on 3 images. In fact, 2 plus 1, 3 images. So quite spectacular difference now. And the images were acquired in a hard way, as you say. So somebody in the building had a TV camera, and they had bought a frame grabber, which they had put in a computer. And so you would have to ask pretty please to acquire one image. You would go there with a book on which the image was. They would put it under a pane of glass. They would capture it. And even printing images was not easy. So there were the first PostScript printers. And I remember that Trevor Darrell at MIT had hand-coded a way of converting JPEGs. In fact, they were not even JPEGs. They were a different format into pictures, into dots of different scales in PostScripts, and those dots would make it darker or brighter. And so I had this piece of software that I would use that Trevor had given me that would convert the images into these raster of dots of different dimensions in PostScript, and that's how we generated images for the papers. That was quite a lot of work.
Yes. So the field's grown up with the hardware, and now it's, of course, dominated by these deep learning techniques. We can take this anywhere, but I was wondering, what your take is on deep learning, what's missing, and, how close is that to the visual system?
Yeah, okay, so that's an interesting question. So first of all, deep learning has been a godsend, I find. Suddenly things started working, and we have primitives that we can work with in vision, and our earlier primitives that were handcrafted wouldn't work well. So of course, deep learning has been around for a long time, and basically Jan LeCun had been at it from the 80s, and he had this great vision, which I believed in. So I was teaching deep learning, or at least Lenet, in my classes since the late 90s, and was convinced that they were really useful. Nobody knew how far they would go, and so in some ways, deep learning was there all along, and but it took GPUs and large annotated data sets to realize that it was also for real, and it could do a lot of work for us, which now we benefit from. And so I guess that, so what's the situation now? So first of all, using deep learning, we can do a lot in practice. And somehow people are now so giddy with what they can do that they think that all the problems are solved, but they are not, clearly. There are many things you cannot do, but you can do a lot. It's still behind biological vision in the efficiency of learning, as we were saying before, because While if you have enough images, in many domains, deep learning has shown that you can do better than human experts. And so we know that in classifying skin lesions or birds and many other domains, you can do better than human experts if you have enough training images. But the number of training images to achieve a certain level of performance is more favorable to humans still. So humans can do a lot with 5, 10. And how can they do it? And so of course we can we can pontificate on how they can do it, but the point is coming up with a computational approach that will mirror that ability. And I have no doubt that we are coming up with it slowly, right? In the next 10 years we'll manage it.
Right.
So now there are many things we cannot do. Like we don't have. We were talking about iNaturalist earlier that can learn from the crowd, but it's not a completely open universe. It's so it can learn a lot of things, but for example, it doesn't by itself separate out the flower, the species of a flower, and the bee that is on top of a flower in a given picture. So it will learn that pattern, and it doesn't know that it's the pattern is either the bee or the flower or the ensemble of the two. So we still need to give our machines the ability to see objects and to separate out the foreground and the background, and to deduce the body plan of animals, the structure of plants. And so there is a lot of structure that is missing, so that the learning is holistic. And so right now you can think of deep learning as a way to do very smart pattern matching, where you can interpolate between patterns you've seen before, but you cannot extrapolate yet. And so
right, it's a great associational machinery, but many things I think are missing. For one, and this gets back to some of your early work, is in a sense, deep learning is an equilibrium approach. You learn, you are learning with a gradient, but in the biological vision system, it's very dynamic. This goes back to the anisotropic diffusion. You get all kinds of optical illusions, color constancy, and color bleeding through, and so there's a lot that's missing in the dynamics of vision. And the question is whether it's a feature or a bug of, is it a necessary part or is it just a biological limitation? I don't know.
Right. Yeah, and also signals in time. We don't yet have the right computational tools, for example, to understand behavior. And that's something that interests me a lot. And I work with colleagues at Caltech, David Anderson, Michael Dickinson, Marcus Meister, in looking at how, using camera, how you can decode an animal's behavior. And so there again, we can classify patterns. So if there is a behavior that is highly reproducible, and whose time scale is fairly constant. For example, there is one action that flies do when they attack each other. It's called lunging. They stand on their back feet and then they lunge forward. So that takes always the same amount of time, and it's easy to then spot it and classify it using a recurrent network. But if you think of more complex behaviors, like the idea of loading the trunk of your car, or foraging, or courtship even in animals, that's highly variable, and it has to do with what you spot is the interaction between multiple agents in that case. And truly, the human visual system infers a goal for the action. And so this idea of inferring a goal and understanding the cause and the effect in a video of what happened and why. So that's still beyond the reach of the computational infrastructure we have at the moment, and we need to think very carefully about how to do it.
And I guess just pure association. Of course, people are moving beyond this, but when you look at a lot of optical illusions, a lot of them derive from the fact that we're looking at something in 2D but interpreting it in 3D. and so like you've studied a lot of this like classification of putting things together, but I think there's also somehow we form a model of the world, and the difference in seeing and perception is the seeing is the input, but the perception's what we make of it. And I think we see in a model, we understand an animal as a 3D object with certain forms. I think that also helps the speed of learning, but it's not actually clear. Well, to me, maybe it's to you, how to represent that, as in an algorithm.
Absolutely right. Yeah, I suspect that the human visual system, at least, has the ability to represent scenes at multiple semantic levels, if you will. Uh-huh. So you could have a pattern of the keys on your desk and you just pick them up. But at some level, you also understand the keys as rigid objects and how do they rest on top of each other, and the fact that if they were in a different configuration, they would fall down and all of that. And so indeed, you could think of an ongoing modification of your model of the world, and the fact that vision is not just this input-output process, but it's deeply tied with the body of knowledge that you handle in your brain. And so vision is there to modify this body of knowledge or to instantiate some aspects of the body of knowledge. And that's another one, thinking of a visual system as a system that is always on, it's always digesting things, it is curious, so it wants to see more. And if you see how children or even animals work, they keep going around and looking at things and picking them up and so on. And so that's another place where we are far behind. And so,
well, it's also, when you dream, you're seeing the model, right? I like to say, like, when you wake up, the dreams don't end; they just connect to the external data. Right?
That's right. Well, yeah, sometimes they end, but yeah. But anyway, so I don't need to tell this to you because you would be, an even bigger proponent than me. But the whole idea of having an embodied visual system that is on top of a machine that can go around and manipulate the world and interact with things and learn from that, that's a very interesting question. So right now I'm exploring this a little bit in the context of biology. I have an experiment going on with Marcus Meister where we put a mouse in a little cage, which is its home. I'm exploring the question of an embodied visual system with my colleague Marcus Meister, who is a biologist at Caltech. And we have a preparation where a mouse lives in its own box. It's a typical vivarium for mice, but the box has a hole, and through the hole there is a tunnel that takes the mouse into a maze. And the mouse can go and explore the maze whenever it wants. And we can put little rewards for the mouse in the maze, like a little fountain with water at some point. And we can see how the mouse, what are the strategies that the mouse uses for exploring the maze, and what does it know, and what does it remember, and does it build them up or not, and so on. It's very interesting. And it's quite clear, I just don't want to, without giving you all the story, but it's quite clear that the mouse is under this immense force, which is this zest for exploration. And it's not going to stop there. And it almost never rests. It wants to go and explore, and once it has explored the whole maze, it will patrol the maze to see if anything comes up that is new. And certainly it spends more than 60% of its time in the maze and not in its home cage where it gets food and water. It just wants to explore. And so it's pretty clear that we need to understand how that works as well. And vision is, of course, a starting point, but it's not the whole story.
Right. And so it's a fascinating area. I tend to call it robot philosophy because I think by building these models, you learn like some of the constraints of making a mind, and it has a lot to say about, the nature of what it means to be us and, animal or human, what you can see and what you can make out. Again, it also gets back to these visual categories, like, color is an example of it's something that's in our mind, not in the world, and and I could go on and on about that, but I wanted to move on. Like earlier, you said, and maybe this is a moving on from that. You discussed art, and it always interests me how some, like, you go to these early paintings and how you could see they understood things about the vision system, maybe just intuitively, but I don't know if you can comment on your thoughts on the learning about vision, and then and how it comes out in art. I also wonder, like, everything humans make, a car has a face. Now, is that just a mechanical thing, or are we reproducing the head of an animal on our technology?
Right. Yeah, so I've studied three things in art. So every 5 years or so, I get some idea and I explore it. And typically I don't do it with students because first of all, the students in engineering are not interested, and then I don't want to make them do something that is going to be highly unpopular. Indeed, anything I've written about art and vision has not been very popular, and yet it's one of those things that you're really happy you did, whether or not people pay attention, it doesn't matter. So one thing was with one of my earlier students, Jennifer's son, and so this had to do with shape perception, shape from shading.
Yes.
So at the time, it was very unclear how shape from shading works, but we wanted to know how quickly people perceive shapes and what's the effect of shading on perceiving shapes. And so we're talking about 95, 96. We looked at the effect of the light source direction, and we realized that people perceive shapes best if the light comes from the top left. Okay, top left of the space in which you are, and we related that to handedness. So we found that left-handed people prefer light on top, a little bit to the right, and right-handed people prefer light from the left. So that seems to be an effect of learning, and that explains to you why all of the little buttons in your GUIs are lit from the top left. And so we also did a survey of paintings and classical paintings in museums, and they all, 85% were lit from the top left. So we figured that and you perceive it much faster if it's top left. So we explained a little tiny bit of art, and if you talk to artists, they're not really aware of this. They just use this convention, and it just works for them. So it's a tiny piece of science that explains to you why art is made the way it is. It's not deep from the point of view of an artist. Another thing that I looked at is how portraiture works, and so it turns out that you can take a picture of. So suppose you have a camera, you have a zoom lens. I can take your picture. If I stand 8 feet away, I can fill the frame with your face, or I can come closer 2 feet away. I can fill the frame with your face with a short focal length. How do I choose? Why do I choose one or the other? And so I realized this because, I became curious about this because I realized that there were some portraits made in the Renaissance where people were really fussy about perspective. And these portraits are famously incongruous in terms of perspective. The face, the shoulders, the waist, the shoes are portrayed from different points of view. And I was wondering, why would they make this mistake if they knew precisely what they were doing? And so it turns out, so if you run psychophysics experiments showing to people photographs taken from up close or far, and these photographs look the same because the face fills the frame, but in fact they don't look the same. There are tiny systematic differences. And so a face from up close, you see the nose looks a little bit bigger, and you don't see the ears very much at all because they're blocked out by the cheeks. While if you take a photograph of a face from far, then you see much more of the hair, much more of the ears, so much more of what is around the face, and the face proper becomes a bit smaller. And people respond with emotion to these faces. And so if you ask them, well, judge, rate this face, how smart does this person look, or how trustworthy, or how how intelligent does this person look, and how approachable do they look. There are systematic differences for faces that are portrayed from up close or from far. And it turns out that if you want a face to be approachable and readable and talking to you, you have to take the photograph from up close, to the point that the person that you're photographing feels that the face is almost a little bit too caricatural, but that's how your friends, your close friends and family look at you. Well, if you want the face to look more impressive, intelligent, but a bit forbidding, then you take the photograph from far. And so it turns out that if you want to make a standing portrait like they would do in the Renaissance, or even an equestrian portrait in which you have to show the entire horse and the rider and the head of the rider and the armor and all of that, well, if you take true perspective and you image the person from far, well, the face will be seen from far and will not look approachable. It will look forbidding. And so if you want to the viewer to feel close and almost in a conversation with the portrait, then you've got to take the entire picture from far, but then you have to paste in a face that is viewed from up close. And that's why you see inconsistencies in perspective. Okay, so that was another thing I realized and I worked on for a while. Another one is the one, okay, so there is another story which is maybe interesting for now because people are spending so much time on Zoom. And the question is, suppose that you want to have a whole lot of people on Zoom. Suppose that there is a family dinner and an old aunt needs to be patched in, and so you want to show everybody on Zoom. Well, it's impossible, right? It's there is no point of view where you will be able to portray everyone. And so the single viewpoint camera, which we love and we use all the time, is singularly inadequate to make somebody feel like they're there with you. It's simply impossible. And yet, painters have faced this forever. So if you think of The Last Supper, it's precisely the problem of patching in an old aunt to a Seder dinner or whatever, in which there are lots of people around the table. And you have to make them all look close and visible and easy to talk to, and they shouldn't block each other out. And so the painters figure it out. And so how do you do it? And so again, you've got to basically make a mosaic of individual viewpoints, and then you stencil them into a common picture. And so I think that Zoom and all the video conferencing tools will have to evolve towards that idea. But anyway, so this is a project I did with Lichit Zelnik, and so we looked at how do you make people feel like they are there. And you have a single picture, and yet the picture allows you to walk through a room or to see things from different viewpoints. And so we were very inspired by David Hockney's mosaics. He calls them joiners. I don't know if you've ever seen these collages that David Hockney makes. And he looks at the same object from different points of view, and he takes pictures and he pastes them together. And so we wondered, is there a way to do this automatically? And so we built a system that could automatically take many points of view on the same object, but combine them into a single photograph that makes you feel like you're there and you can explore without the image changing. And so something I realized, which is surprising to some extent, is that your visual system is very robust to these inconsistencies. And you're perfectly willing to take multiple points of view. Maybe your face will be seen many times with different expressions, and you can use your visual system as a window to go back, and so you take it in as a sequence in time, different moments, different aspects of the same scene, different viewpoints. And so what we were saying before, which is your visual system is enabling you to construct a model of the world, is precisely true. And it's able to do so even if the image is not a single viewpoint perspective, which is what we are training our algorithms to see. And so that's another place maybe where computer vision systems can improve, how to combine different views and acquire knowledge.
It's too bad more students aren't interested in this. I've always wondered, I've noticed that with medieval portraits that they often do have, like you look at an alleyway and that's actually a point of view. It's not as if there was one camera and then the person is a point of view. I always thought it was related to visual attention. Like you're there in the scene, that's what you would observe. You would look at one direction, then you would look at another, and that would be the focal point of your attention. So it kind of puts you in the scene more than making the portrait as if it were just a camera photo.
That's right.
That's a fascinating area, art and the mind. I wonder if we could start talking about where you see computer vision going, or what's coming next. What are the current uses? Again, looking back, it's hard for people to realize that, like when I started out, when I first met you, hardly anything actually worked, right? And now it's gotten to the point where it's a real tool. Like I'm running this contracting, and we can say yes to most things. Like, yeah, we can do that. But before, I would have no idea, right?
Indeed. Yeah. Okay. So just to recapitulate a few things that, so you're asking, where is computer vision going to go? To recapitulate a few loose ends that we clearly see now. So there are fundamental questions like, how can computer vision systems learn more efficiently? So given fewer training images, how can it become our helper and not a ball and chain in which we have to, when we want to start doing something, we've got to spend months collecting images and annotating. And we would like to get going right away. So how can you train a computer vision system like you would train a smart child? This is a dog, you just see one, and we've seen them all. Okay, so that's one. And it's a fundamental capability that will help us throughout. The second one we're saying before is cause and effect and intent in video, also in still frames. So how can we understand the interaction of objects, of agents like humans, animals, vehicles, and how do we infer intent and agency from sequences, and causality? So that's another one that is big. And so I should remind people that again, machine learning is so helpful, but machine learning as it is now is good for prediction because it's looking at correlations, but it doesn't understand causation. And so it's not good for intervention. So if you want to have machines that become active in the world, you've got to understand the effects of intervention. So if you see that every time that people have their umbrellas out, it rains, it's not true that by asking people to close their umbrellas, you will make the rain stop. You've got to understand which way the causal arrow goes. And vision today doesn't get that signal, it's not able to do it. And so the third one is, as we were saying before, vision in the loop. So you have an agent that trains itself by interacting with the world. It has curiosity, it has volition. And so going back to causality, it is able to carry out experiments, which are the only way really to establish cause and effect. And so you would want to see agents that play with objects and let them roll down and fall and all of that, to teach them how to interpret the visual signal in order to infer cause and effect, and therefore being able to influence the way the world is going. That's another one. Now, another one is vision is maybe the most informative sense we have to discover the world. And so humans use vision all the time. And there are entire branches of, say, medicine that depend on vision, like radiology, like pathology, like ophthalmology. Dermatology is another one. And so how do we combine the knowledge of humans? How do we combine images? How do we combine algorithms in order to achieve what they call communities of knowledge, which is enabling people to exchange information more efficiently, to train each other, to let reality or let the truth bubble up from the data and from multiple sources of expertise. And so how can we put a machine at the center of a community and make it more efficient, effective, knowledgeable, and discover what it doesn't know also. And so how can machines help people distill knowledge? This is, and so vision plays a big role there, and it's another one. So these are my big ones, and I'm sure there are many more, but these are the ones that I think about.
Okay. We're getting close to an hour here. Are there things we haven't brought up that you want to talk about, or current work, current students, whatever?
No, these are all. No, I think so. One thing that worried me when things started working out is that soon we would saturate the things we can do with vision, and it will become much more of a routine. And indeed, you see a lot of routine papers out in conferences right now of trying different variants of a certain deep network, and that work is really useful and needed, necessary. But I became a bit concerned that maybe vision would not be as much fun. There would not be as many open questions. But the more I think about it, the more I see open questions still, and I think it's a field that is going to go on as a lively, interesting, intellectual area for quite a while. And so we have to allow the boundaries of what we want to do to become bigger, so to be more hungry for more. We have to be willing to change somehow modality of operation, and so as we were saying before, put humans in the loop, build machines that have vision in the loop, and so on. So this in the loop thing, interactive, and so on, is really interesting. It's very difficult because when we carry out experiments using large batch data sets, it's so simple. We run the experiment, we change a couple of parameters, run the experiment again. We've burned through a few kilowatt hours of energy, but it's easy to do, and the results are experimentally solid. And if you want to do experiments with people in the loop or machines in the loop, then every experiment is a story of its own, and it's very difficult to see what caused what. And so that will be slower progress, but it's really worth investigating. So these are the things. Maybe I should say one more thing, which is so another thing I've realized recently is, again, going back to annotated data sets, when we do what we call an experiment, it's really an observational study. Namely, we collect pictures from the world, and we annotate them in different ways, and then we see how well our algorithms perform on them. But they're not a real experiment in the sense that we can control variables and we know what is the effect of a given variable on the results of the experiments. And this is coming out, I would say, very compellingly now that people want to know, for example, if vision systems have biases, for example, racial bias and visual recognition of people or face classification or whatever. And so you see people collecting data sets and annotating them and publishing results and saying there is bias or there is no bias, but truly we don't know, because those data sets are observational, and there are so many correlations that go on with gender, ethnic background, and everything else. For example, there are these celebrities data set that people use, and one simple correlation is female faces are much younger than male faces. And why? Well, probably because females have an earlier career in the show business, and for men it takes a bit longer to develop, and they are viable for longer than females and so on. But there is a big age difference. So when people say, it works better for females or for males, well, is it because of the gender or because of the age? Well, people don't think about that. And so we have to learn how to carry out experiments, to control the variables one at a time, and in order to be able to make causal statements like gender change will make the algorithm perform less well or better, or a change in age will cause more errors or less errors. And so we need to learn how to do experiments, and of course it's very difficult. And so that's another challenge we have in front of us, if you just to list another one.
Right. Well, in bias, it's clear, any embodied or purposeful activity has a bias to achieve that purpose. So a lot of that is reflected in data sets. If you're taking wedding photos, you're going to center the people and do all this stuff. It'll have a bias in that way. If you're attempting to fight crime, you'll get a bias because of what you're trying to do, where you're trying to do it.
Yes.
And
so that's something we have to learn how to recognize and to dissect, the bias in our data sets and how to, and it will take time because it's not self-revealing, there is no theorem, there is no
right,
technique.
to somehow make it transparent what the biases are, because everything is biased, right?
There's right, no question. Yes.
Okay. Any final words?
No, so the field is a lot of fun. I think that young people who enter computer vision will enjoy it a lot. If, like me, they enjoy images. If they're willing to work on problems that are not completely well formulated, and yet you can take the challenge and see if you can clean them up and ask the right questions. Working in vision forces you to come in touch with many different fields, from physiology to art to geometry to physics,
medicine, everything,
to computation, medicine, and there are all the fields of application. So it's lots of fun to get your hands dirty and to help other disciplines be successful. And so the call for new bright people to come in is open, and I think the people. It's a good investment of a lifetime to work in this field, and I hope that people will have as much fun as they've had so far.
Way back, I used to feel guilty. Way back, I was attracting people with my research and library into vision, and I thought none of these people will ever have a job because it doesn't work. But it turned out just the opposite. None of those people has ever seen unemployment.
That's right. That's right.
Yeah.
Luckily, for us,
Okay.
Okay.
So this has been great talking with you. It's very interesting.
Yeah, thank you for having me talk to you. And so this was fun.
Okay. Bye.